Good evening, everyone. I am Harshit Agrawal, and welcome to the sixth live session of mine for the course Design of Reinforced Concrete Structure offered by NPTEL. I am a PMRF research scholar from IIT Bombay, and I will be conducting weekly live session for all 12 weeks of this course. So just to start with, what is this session all about? So these are doubt clearing session and interactive session. When it will be held? It's a weekly live session by me every Tuesday from 6 p.m. to 8 p.m. till the course runs. How to interact? Either by answering my questions in the chat box or by asking questions in the chat box or by raising hand, unmuting and asking your queries. Apart from live session, you can always use the discussion forum of the course to clarify your doubts, the answer to which will be given either there only or in the upcoming live session. Through these sessions, you will be able to answer weekly assignments easily and will also provide you further understanding about complex topics holistically. So I hope everyone are clear about the session. Now in today's session, we will first have a look at what we discussed in the last live session that was for week 5 of the course. Just a quick glance. Then we will discuss week 6 content, wherein today we will talk in detail about the design of two-way slabs. So, in this, we will first revisit our discussion over two-way slab design done till now. Then we'll see how reinforcement detailing is done, and then we will solve 2 to 3 numerical so that everyone is clear up with unrestrained and restrained slab design, and finally we will conclude the week. So in the last live session of mine we started our discussion over design of slab, wherein we first saw the basics of slab design in terms of application and in terms of technical definition. Then we looked into IS 456 provisions in terms of for four key parameters: slab parameter, design parameter, effective span, load distribution, bending and shear coefficient, and deflection control. Then we discussed deep into design of one way slab, where it is used, and a numerical for design. And finally we talked about design of two way slab, uh, which we will recap again shortly in today's class. So this is just a correction. Okay. So just to recap, discussion on two-way slab, slabs that are continuously supported in both the direction on all four sides and are such in dimensions such that the load are carried to the support along both directions. So how we define two-way slab? The slabs in which load is carried along both the directions. Okay, so there are two directions. This is x direction, this is y direction. In both the direction, the load will be distributed, and for these slab, the floor support is provided continuously on all floor side. And when we say the slab is two-way slab, when the ratio of longer side to the shorter side is less than 2. Okay, so they are made to span along both longer side and the shorter side. Okay, and in this we provide, since it is spanning in both the direction, we provide reinforcement along both direction to resist the bending, and generally where it is used in multi-story building floors and ceilings. So we saw a one-way slab is mainly used in verandas and chajjas, and two-way slab is generally used in floors and ceiling slabs. Okay, so if we see how this bending happens in two direction, so if this is my slab, so it's not like the whole load that is acting is causing bending deflection in both the direction. Why not? Then there will be so many points at which we need to design twice the amount of load. So uh, that's why we talk about load distribution. So see, if this is my slab and on the top the load is acting, my bending can happen in both x direction and y direction. So if I pick this point And if I consider a point load here, this point load, it will cause deflection in x or y. That we need to define clearly, because all the load won't cause deflection in both the side. That will make design uneconomical. Okay, so for that we need to talk about load distribution. So when we talk about two-way slab, as you can see in this figure, the load is acting over the slab is divided in the pattern as shown in the figure. So the load acting in this area will correspond to this side bending. The load acting in this area will correspond to this side bending. Similarly, this area and this area. Okay, so this is how load are transferred. Okay, now how this load is divided and how to get the factor of how much load is there in x direction and how much load is there in y direction this. So that we get from IS 456. So just to simplify these things further on, based on the type of slab, IS code divides two-way slab into two categories further based on the support condition. So first is the simply supported two-way slab. What are simply supported two-way slab? If there is no restraint at the edges. Okay, so these are my supports. Suppose these are my four supports. So if there are no restraint on the supports, then we say that there is no restriction for torsion at the corner, and the corner can lift. So such slabs are known as simply supported two-way slab. Okay, and in these this coefficient of how much load will be acting in x direction and how much load will be acting in y direction, the coefficient, the factors of which we get from table 27 of IS 456. Okay, so depending upon the ratio of Lx and Ly, we can get the value of Ax and Ay, alpha x and alpha y. Okay, now, this statement that is written here, we will see later on what is the meaning of this statement. 50% tension reinforcement provided in the midpan should extend to the support, and remaining 50% should extend within zero point 0.1 Lx and zero point 0.1 Ly of the support. This statement we will see later on today in the class when we will talk about the reinforcement detailing. And secondly, we have restrained supported two-way slab. So these are the slab in which the corners, not all the corners, but some corner or all the corners are restrained from lifting. So such slabs are known as restrained supported two-way slab. And in these slab, since the corners are prevented from lifting, there can be some torsional action also acting at the corner, for which also we need to provide some reinforcement. Okay, so since slabs are restrained, apart from the moment near the midspan, there will be some negative moment that can also arise on the support. So based on these, there can be four factors. In x direction, there can be a positive moment factor, negative moment factor, and in y direction, there can be positive moment factor and negative moment factor. So these are given the alpha x, alpha y, and alpha y. Now, based on how many sides are restrained and what is the continuity of other sides, there can be nine cases of restraint supported two-way slab that are mentioned in this figure. Okay, so you can see the ninth one, which is four edges are completely discontinuous, and you can see the first where the all the edges are continuous, two edges are continuous, two long edges, two short edges. Okay, so based on this, we can classify a restraint supported two slab into nine categories. Okay, now for all these nine categories, IS code defines the value of alpha and alpha x and alpha y. So these are the values how you get alpha x and alpha y based on the restrainment. So if I have an interior panel, what will be the case? If I have a four edge discontinuous system, what will be the case? If I have a two edge discontinuous, two short edge discontinuous system, what can be the case? I need to please unmute yourself. Thank you. Okay, so these are the nine cases that we have talked about in the last class also. Now, just to understand the complexity of reinforcement designing in a better way, so if we consider a continuous slab we design for tension reinforcement, now what code says, so this is the tension reinforcement that we generally design for. Now what code says that near support you need to provide some reinforcement in the compression side also. Now how to do that? For that, for end support, from a distance of 0.15 L1 we start bending the rebars, alternate rebars from the tension side, such that point 0.1 L1 is the length of the rebar on the compression side. Okay, so from point 0.5 L1 we will start cranking the rebar such that we'll get a length of point 0.1 L1 at the compression side near the support. Okay, so if my total reinforcement area is AS1 in tension side, I will say 0.5 times AS1 will come in the compression side when I'm talking about end support. Okay. For mid support, these value changes, these value of 0.15 and zero point 0.1, these factor changes to 0.25 and 0.15. So from a distance of 0.25 L1 from the support, we start cranking the rebar such that the length on the compression side till the mid of the support is 0.1 L1. Okay, 0.15 L1. Okay, and we extend this 0.15 L1 to a area of 0.15 L1 on the other opposite side of the support also, just for safety reasons. Okay, so it is like 0.25 L1 from the support, and the tension side we crank the rebar and till the length of 0.3 L1 across the support, across the mid-span support, we provide the reinforcement at the top. We won't go further deep into this since these all are guidelines that you can directly find the code also, or in the SP16 guidelines also. But just to make you clear how cranked rebars are provided, I explained a bit. Okay. Now, when we talk about restraint support, there is torsional stresses that are generated, that can be generated near the supports also as a result of restrainment. So for this, what code says, we need to provide steel mesh. So you can see these are steel meshes. Okay, now how to design for it? So for end support, the area of steel mesh required is 3/4 the area of steel that we provided in the tension side. Okay, the area of main reinforcement. So 3/4 of that we need to provide along x direction also, and 3/4 of that we need to provide along y direction also. And up to how much distance? Up to a distance of Lx by 5. So shorter length upon 5. This is the distance till which I need to provide the steel mesh along both the direction. Okay. So knowing the area of one rebar, suppose I am using a 8 mm rebar for mesh, we can calculate what should be the spacing. So I have AS1, I know the total area 3/4 of AS. Okay, so from this I can calculate what should be my spacing. Okay, if I want to calculate the spacing between these mesh. Okay, and when we talk about mid span support, the area that needed to be provided changes to 3/8 of the area provided to main reinforcement. So just remember these values from IS 456 guidelines while designing. Okay, so this was complete discussion that we had this week, mostly regarding the reinforcement detailing. Now we will focus on different types of numerical that can be framed based on the design of two-way slab. Okay, so this is the first numerical. What this numerical says: design a two-way slab with given detail: M20 grade concrete, Fe 500 grade steel, center to center distance of long span is 4.85, center to the center distance of shorter span is 3.15. Boundary conditions are one edge, one short and discontinuous. Assume floor finish load of 0.5 kilonewton per meter square and live load as per the criteria of office floors. Okay, so we have given all the condition. This is the slab that we need to design. So you can see one short end is discontinuous, so this end is discontinuous and rather all end are continuous. Okay, so for this slab we need to provide the detailing. So I will mute myself now for 5 minutes and give you guys time to try to start solving this question on your own, and then I will tell the solution. Okay, so let's see the solution now. I will take a new slide. Okay, so given things in the questions are, I hope I am audible. Yeah. So it is given M20 grade concrete, Fe 500 steel. Okay, so and Ly longer span length is given to us as 4.85 meter. Lx is given to us as 3.15 meter. Okay, and boundary conditions one short and discontinuous. Okay, so our step one always is to check which kind of slab is this. Right now we know, but still we will check. The step one is to check the type of slab. How to check it? By calculating Ly by Lx ratio. So my Ly by Lx is nothing but 4.85 divided by 3.15. So it will come out to be 1.54, which is less than 2. So I can say slab is a two-way slab. Okay, now we will start the designing. So first, now the second step is to provide dimensions. Okay, now generally, since my shorter length is less than 3.5 meter, and live load as per office load criteria would be 3 kilonewton per meter as per IS 875 guidelines. So what code says, your ratio of longer length to the effective depth should be 30 when you are talking about continuous slab. Okay, so since there can be some modification factor also, I will consider thickness of slab as the shorter span upon 32. Rather than 30, I am taking 32 just for safety. So this will be 3150 divided by 32. It will come out to be 98.4 mm. Okay, now practically it is not significant to provide this. So I will take total thickness D as 120 mm, and suppose clear cover is 20 mm, and I am using 8 mm diameter rebar. Okay, so my effective depth will become small d will become 120 minus 20 minus 4. Okay, d by 2. So it will come out to be 96 mm, which is close to what we assumed. Okay, so I got my effective depth value. Okay, now next part, I will just update everything that we have done here again. So capital D is 120 mm and small d is 96 mm. Clear cover is equal to 20 mm, and diameter of main reinforcement is equal to 8 mm. Okay, so now we'll see the next step. So step 3 is our load calculation. Okay, so what is dead load? What it will be? So it will be nothing but 25 kilonewton per meter square that we consider for concrete into 0.12 the thickness of a slab into point 1. that we generally consider the width of the slab while we are designing. So it will be 2.5 kilonewton per meter. Okay. Live load. So for office floors, as per IS 875 guidelines, it is 3 kilonewton per meter. So 3 into 1, that is the width of our floor. So it will become 3 kilonewton per meter. Okay. Now one load floor finish that is given to us. So floor finish load, it is given zero point 0.5 kilonewton per meter square. So zero point 0.5 into 1, it will become zero point 0.5 kilonewton per meter. So total load is sum of 3, which is, here it is 3. So it is 6.5 kilonewton per meter. So my factored load will become 1.5 into 6.5. It will be 9.75 kilonewton per meter. Okay. So based on this, I can calculate the moment. Okay. So my step 4 is moment calculation. Okay, so how I can calculate movement? So for continuous slab, the support end possesses negative movement and the middle strip is subjected to positive movements. Hence, negative and positive movements can be determined along both shorter span and longer span. And this we can calculate from IS 456. Okay, so MUX is nothing but alpha x WU into LX square, and MUY is nothing but alpha y WU into LY square. My LY by LX ratio, what it is? 1.54. Okay. So based on these guidelines, okay, one short end discontinuous. So which is my case? So the second case. No. Second case only, one short and discontinuous it would be. So based on that, you can calculate Lx and Ly. So you need to interpolate. Ly by Lx ratio, it is 1.54. So between 1.5 and 1.75, you need to do the interpolation. Now I will tell you the final value because these are all basic mathematics. So alpha x positive you will get as 0.069, alpha x negative you will get as 0.052. Similarly, alpha y positive you will get as 0.037, and alpha y negative you will get as 0.028. Okay, so these are the moment values that you will get. Now we'll calculate these are the coefficients. Now we need to calculate the moment from these coefficients. Okay, so I will just update here. Factored load is 9.75 kilonewton per meter. Okay, so we'll do the moment calculation now. So we know alpha x, alpha y, and everything. So mu along shorter span, mu negative will be 0.069. Okay, this is negative and this is positive. Okay, my mistake. This is negative and this is positive. So mu negative will be 0.069 into 9.75 into 3.15 square. So it will come out to be 6.67 kilonewton meter. Okay, similarly mu positive, it will come out to be 0.052 into 9.75 into 3.15 square. So it will come out to be 5.03 kilonewton meter. And along longer span, mu positive, it will come out to be mu negative, it will come out to be 0.037 into 9.75 into 4.85 square. Okay, so it will come out to be 3.58 kilonewton meter, and mu positive, it will come out to be 0.028 into 9.75 into 4.85 square. So it will come out to be 2.71 kilonewton meter. Okay, so this is how we will calculate moment along all the direction. Okay, now what is the next step? So we have done with the moment calculation. Now step 5. So what we generally do, we check for these moment based on the limiting moment. So check for depths, just to check whether the depth that we have provided is sufficient or not. Okay, so mu limiting, how we can calculate? By calculating xu by d. So right now I'm directly writing the value. When we are talking about fe 500, the factor is 0.333, 0.133. When we talked about fe 415, it is 0.138. So 133 fck bd square. Okay, so this upon calculation, you will get mu limiting. So mu limiting. So in these four value, what is the maximum moment? This is the maximum moment. So we will take as the limiting moment. Okay. So based on this, we can calculate the d value. Okay. So d will come out to be, so mu limiting is my 6.67, which is equal to 0.133. FCK is 20. D is 1, which is equivalent to 1000 right now. Okay, and d square. Okay, this also we need to convert, so this will be into 10 to the power 6. Okay, kilonewton meter, so we need to convert into newton millimeter, because all these values are in newton and millimeter. Okay, so just dividing everything, you will get small d as 44.7 mm, and what we provided 96 mm. So d required is less than d provided. So we are good to go ahead. Okay, safe. We are safe to go ahead. Okay. Now we need to do the reinforcement calculation. So step 6 is reinforcement calculations. So how this is done? By using this equation. I am writing the bigger form of the equation. You know how to simplify it. So 0.87 Fy AST D 1 minus AST Fy upon PDFCK. So this we saw in when we were designing beams. So this is x by d value, how we get by equating the compression force and the tension force. Now after that we write mu value for getting the AST. Okay. So based on this formula, we will first get the AST, and then for spacing, what we will do? Spacing is nothing but area of 1 bar upon total area into 1000. Why 1000? Because 1000 is the width of the beam section that we are considering right now. Okay. So based on this, we get the reinforcement detailing, and later on we check with AST minimum. So minimum reinforcement that we need to provide. So that is nothing but 0.12% of gross area. Gross area is nothing but BD. Okay, so B times B. So substituting value, this is nothing but 0.144 mm square. So when you will be calculating area for all the four movements, that area should be minimum this value. If the area is, say, suppose 100 millimeter square, then you need to choose 144 millimeter square only and then calculate the spacing. Okay, and what is the criteria of spacing? Spacing is should be more than minimum of, should not be more than, should be less than minimum of b times b comma 300. Okay, so based on the values that you are getting, 3 times b and 300, it is 280 mm. So your spacing should be less than this value. Okay, so this is just a brief of how reinforcement detailing is done. Okay, just to clarify everything. Okay, so on applying all the equations, what you will get at supports. Okay, so my mu is 6.67 kilonewton meter. For this, you will get AST required as 165 mm square. When you will substitute mu here, Fy, D and B, FCK, everything, when you will substitute, you will get AST at support as 165 mm square, which is more than our AST minimum value. So we can go ahead. So for this area, what you will get, you can calculate the spacing. So you will, what you will get, your spacing will be 125 mm center to center. Okay, so this is how you will get the spacing. Okay, so this is in along shorter side. Okay, similarly at midspan in shorter side, mu is 5.03 kilonewton meter. So you will get AST as 161 mm square, and your spacing of rebar, 8 rebars that we provided, it can again be 125 center to center. Just try to make sure that you're not varying spacing a lot, so that for in the end detailing is easy. Okay, similarly along longer side at supports, mu is 3.58 kilonewton meter. So your AST will come out to be 113 mm square. Now this is less than 144 mm. So what we'll do, we will provide 144 mm. Okay, rather than what we are getting, we'll provide the minimum reinforcement. And again, you can provide this as a, at a spacing of 225 mm center to center. Okay, for safety. And at midspan, mu is 2.71 kilonewton meter. Your AST will come out to be 66 mm square. But again, this is smaller than the minimum AST that we need to provide. So we will again update this with 144 mm square. And this again we can provide at a spacing of 225 mm center to center. See why I kept spacing same in every direction, so that when I'm actually designing the slab, it is easy for me. If you will try to calculate spacing here, it will come out to be around 350 mm center to center, which is not possible. So I'm choosing a similar value for along all the directions, so that it is safe for us to provide. Okay, so this is how we calculate all the movements along midspan and along support. Now after this, there is one basic thing that we always need to do, that is check for shear. Okay, so that I am not showing because everyone knows how to do that. We know the tau v value. Okay, we know the ultimate load, so we can calculate tau v, we can calculate tau c, and we can check whether shear it's needed to be provided or not. So okay, so this we have already done. Okay, in the past classes how it is done. Okay, and finally you can check for deflection also. Since you know how much area of reinforcement was required and how much you have provided, you can calculate the modification factor, and based on the modification factor you can check whether you're allowed support conditions, like allowable depth upon depth, allowable span upon depth that you have provided is enough or not. If it is enough, we say that it is safe for deflection. So check for deflection. That is also we saw in the last class, so you can do it again. Okay, that is a very simple calculation you can do again. Okay, I hope everyone are clear with the calculation. I hope everyone are clear with the last two steps how they are done. If you have any doubt, you can ask. Since we have two more questions today, that's why I'm not showing all the calculation right now, so that we can cover the remaining question also in the same class. Clear? Any doubts? Okay, if this is clear, since you will get the slides also, you can see the solution later on again. Try to do it on your own and check with the solutions that I have provided. Okay. Now we will move on to the second question. Design a reinforcement slab for a room of clear dimension 4 meter cross 5 meter. The slab is supported all around the walls of width 300 mm. The slab carries a live load of 4 kilonewton per meter square and the floor finish load of 1 kilonewton per meter square. Use M20 grade concrete and Fe 415 grade steel. Assume all corners are held down. So this is what it is given in the question to you. Try to think how to solve this question on your own, else in a couple of minutes we'll see the solution. Okay, so let's see the solution now. Now, the the format of design will be the same like how we did in the last question. We will calculate the moment and then we'll calculate the area of reinforcement and spacing, but there are a couple of changes in this question that you need to make sure. Okay, so what it is given, my ly is 5 meter, lx is 4 meter. Okay, so support width is 300 mm and it is supported on all the sides. Live load is 4 kilonewton per meter square. Floor finish load is 1 kilonewton per meter square. Okay, M20 grade concrete we are using and Fe415 grade steel we are using. Okay, so these are the conditions that is given to us. Now, there is an important clause that you need to remember. Okay, step 1 again will be to for slab, check for slab whether it is two way or one way. So right now we know it is two way. Okay, we won't do that calculation again. Step 2 is to provide dimensions. Okay, now see, as per is code, there is two things that you need to look when you are providing dimension: the lx value and the live load. Okay, if my length of shorter span is more than is less than 3.5 meter, if this value is less than 3.5 meter and my live load is less than or equal to 3 kilonewton per meter square, then we need to use the clause. Okay, I will just mention here so that later on it is easy for you to recall. If this value is less than 3.5 meter and live load is less than or equal to 3 kilonewton per meter square, then you need to use the clause number 26 point, that is 24.1. Okay, clause 24.1 for choosing the ratio, lx by d ratio. Okay, for uh, calculating effective depth you need to use clause 24.1. If this is not true, then you need to use the same clause that we use for one way slab design. So in our case, this condition is not fulfilling. So what we will calculate? We will calculate the L by D based on one way slab design only. Okay, so this is what it is mentioned in code. Last time it was fulfilling, so we used clause 24.1. This time it is not fulfilling, so we will use the same clause of one way slab design. Okay, now generally for one way slab design, what it saves for simply supported slab, we need to go for lx by d ratio of 20. But since we know there can be some modification factor also, so let's assume my lx by d as 25 mm. 25. Okay, so if I assume lx by d as 25 initially and it will provide me control over deflection, I will get the d value as 4000 divided by 25, which is nothing but 160 mm. So this will be my effective depth. Okay, suppose I am providing a effective cover. Okay, effective cover, suppose I am providing is 20 mm. Not clear effective cover I am talking, so my capital D will become 180 mm. Okay, so this is what I am assuming right now. How I can get this effective cover of 20 mm? I am assuming 15 mm of clear cover and 10 mm diameter rebar that I would be providing. Okay, based on these condition, I got the total depth. Okay, so now what is the second step? So second step will be third step. Sorry. So third step will be to get calculate effective span along all the four direction. Okay, in last question it was not an issue to us, but now we need to calculate that also. So effective span will be nothing but clear span plus effective depth, or clear span plus or center to center distance of the support. Okay, clear span plus effective depth or center to center distance between supports. Okay, now when you will do the calculation, what you will get along x direction, your um, Lx effective will come out to be 4.3 meter. Okay, and along y direction, your Ly effective will come out to be 5.16 meter. Okay, how you will do this calculation? Simply by calculating these two values. Okay, clear span plus effective depth and clear span plus, okay, this will be again, this will also be 4.16 mm. So in both the cases you will find this is the limiting value. Okay, this will give you a higher value, this will give you a value of 4.3 mm and 5.3 mm, and this is giving you value of 4.16 mm and 5.16 mm. So I will choose this. Okay, now, once you get the effective span, you know the depth of the support and you know the width. The fourth step will be to calculate loads. Okay, so my self weight or my dead load will be nothing but 25 into 1 into my width, which is 0.18. So it will come out to be 4.5 kilonewton per meter with me, sorry, depth. Okay, floor finish load it is given as 1 kilonewton per meter, and live load it is given as 4 kilonewton per meter. Okay, so based on this you can calculate total load, and my factored total load will come out to be 1.5 into sum of these three, which is nothing but 9.5. So you'll get a value of 14.25 kilonewton per meter. Okay, any doubt, Deepak? If you don't have any doubt, you can mute yourself. Okay, we get the factored load value. Okay, now the slab is simply supported on all the four sides since it rests on the wall, so corners need to be held down by torsional reinforcement. That is what we have seen. Na? Assume corners are held down and the slab is supported on all the four sides. Okay, so we know the case. So all four edges are discontinuous. So this means that we are belonging to this case 9. All the four edges are held down, all the four edges are simply supported, so we need to go for case 9. Now for case 9, how to get the alpha x and alpha y value? So we have a single value of alpha x and alpha y, so we can calculate our Ly by Lx ratio now, and based on that we can calculate alpha x and alpha y. So how to do that? Okay, so my Ly by Lx, if we see from the calculation, it is 1.24. Okay, so I know for 1.2 what is the values, 1.3 what is the value, so I will do the interpolation. Okay, so what I will do, I will get alpha x value as 0.0748 from that table, and alpha y value I will get as 0.056. Okay, you can see here in the table. Okay, my alpha y value is the same for all Lx and Ly, and alpha x value, so 1.54. So I will do interpolation. Okay, and I will get the value. Okay, for 1.24. Okay, so for 1.24 I will do interpolation between these two values, 0.072 and 0.079. So when you will do the interpolation, you will see you will get this value 0.0748. Okay, now since you know alpha x and alpha y, what you can do, you can calculate moment along x direction, which will be nothing but alpha x 0.0748 into WU 14.25 into LX square. LX square is nothing but 4.16 square. So it will come out to be 18.446 kilonewton meter. Similarly, My you can calculate. It will come out to be 0.056 into 14.25 into 4.16 square. Okay, so it will come out to be 13.809 kilonewton meter. Once you get mx and my value, what you can do, you can provide the reinforcement detailing. Okay, now the remaining question is very simple. Okay, that reinforcement detailing part, everyone knows how to provide the similar way how we provided in the previous question. So reinforcement detailing. So for that you need to go for the thing that we read in the beam design part. How to provide reinforcement detailing? We will calculate AST. So along x direction, when you will calculate AST, you will get, just let me check the calculation once. Okay, along x direction, your AST will come out to be 348.90 mm square. Just do the calculation on your own, you will get this value. Okay, so since we assume 10 mm rebar, so we'll provide 10 mm diameter rebar at the spacing of 225 mm center to center. Okay, this calculation you can do. In the last question, I told you all the basic formulas that you need to opt for when you are designing. Okay, then you will do the calculation for reinforcement along y direction. So along y direction, you will observe ASTY will come out to be 264.66 mm square. So this is the reinforcement that you require. So you will provide in along y direction, you can go for say 8 mm rebar. So 8 mm rebar you will provide at a spacing of 180 mm center to center. Okay, this, how to choose this? This is upon you. You can also go for 10 mm rebar, but when I did the calculation, I opted for 8 mm rebar. So this is how we do the calculation. You need to check the spacing criteria with 3D and 300, whichever is less, and you need to do the safety check. Okay. After this, what we do? After this, we check for L by D. Okay, so once you know what AST you have provided and what AST you require, you can calculate the modification factor, and you can check whether the L by D that we have opted, it is safe or not. So when you will do this calculation, you will find it is safe for design. Okay, that is very basic, so I am not telling again. So this you can do. Now what is the main part here? The main part is the design of torsional reinforcement that I wanted to show you in this question. Okay, so how we design for torsional reinforcement? We know the size of the mesh is nothing but Lx by 5. So it is Lx by 5. Lx we know it is 4.16 divided by 5. So it will come out to be 832 mm. Okay, this is meter. Okay, so I will convert it into thousand. So I will get millimeter. So this is the size of the mesh along x and y direction that we need to provide. Okay, and area is 3 by 4 times what we have provided along main direction. So 3/4 of 333.746. So how we'll calculate this area based on the rebar and the spacing that you have provided. Okay. So this value will come out to be 250 mm square, roughly 250 mm square. So you know the area. Suppose I am providing 8 mm mesh dia bars. Okay, so I can calculate the spacing also. Spacing S will be given by AS of one area of one steel upon total into 1000. So from this I will get spacing. So suppose the spacing amounts to be 200 mm. It will come out to be roughly 200 mm. So you know the mesh size. Okay, this is the length along x direction and y direction. So if I can just draw once. Okay, so along x direction, my length of mesh is 832 mm. Okay, along y direction, my length of mesh is 832 mm, and I'm providing 250 mm rebars at a center to center distance of 200. So this is how you will provide at the corners mesh. Okay, so this distance is 200. This is 8 mm diameter rebar, and it will run till 832 mm from the support. Okay, so this is how you will do the reinforcement design for the edge strip. Okay, for torsional
सर
reinforcement.
सर अ मिनट टॉर्सनल reinforcement calculation में सर 4 into 16 16 is the dia of bar.
Where in torsional reinforcement,
Yes,
where you read 16.
size of mesh is equal to lx by 5.
Yeah, so 4.16 is my length of
अच्छा
shorter side.
4.16, sorry sir, I got it 4 into 16, that's why I was
No, no,
confused.
it is 4.16. So just remember the clause Lx by 5 and 3/4 the area. Okay, so the reinforcement detailing I hope is clear to everyone. In the last question, we saw how it is done, and now we also understand how torsional reinforcement is provided. Okay, any doubt in the question? If not, let's see the last question. Okay. Design a two-way slab with given details: M20 grade concrete, Fe415 grade steel. Center to center distance along longer span is 4 meter. Center to center distance along shorter span is 3.89 meter. Boundary condition: simply supported with no end state. So this is the simply supported case. Till now we saw the restrained cases. This is unrestrained case. Okay, floor finish load is 1 kilonewton per meter square and live load is 2 kilonewton per meter square. Okay, this must be a simpler question now for you since we have dealt with the restrained cases. So just to tell you one case of simply supported also, I have chosen this question. Try to think about how what are the steps of solving on your own, and then I will just tell you the steps how we solve. Okay, just one additional clause in the question. Assume beam width below the slab as 0.23 meter. Okay, 0.23 meter cross 0.23 meter. Okay, since you will need to calculate the effective length, this is also you need. I will wait for a couple of minutes more and then we'll see the solution. Okay, so just quickly we will go through this question because now we know how we do the load calculation and everything. So I'll just write the steps and I will leave on you to solve this question now. I hope everyone can do the question on their own, right? So What is the step one? This will be a kind of revision for us also. Okay, we have talked about two-way slab design since last three sessions now. So this is like a final revision for you guys. Okay, so always step one is to check for which type of slab it is. How we check? Based on Ly by Lx ratio. If it is greater than 2, we say it is a one-way slab and it is spanning along the shorter direction only, and we provide main reinforcement along shorter direction, and that is it. Okay. If it is less than 2, it is two-way slab. Okay. So in this question, based on the values that is given to us, we can clearly say it is a two-way slab. Okay, 4 upon 3.89, it will come out to be a little higher than 1, which is a two-way slab. Step 2, we need to provide dimensions. Okay, how we do that? When we talk about two-way slab, we need to check for live load and length of shorter span. Okay, so what is the limiting value of live load that we are concerned with? 3 kilonewton per meter square, and length of shorter span, it should be 3.5 meter. If both of these conditions are fulfilled, then we go for clause 24.1, that is specially for two-way slab. If this is not fulfilled, then we go for one-way slab clause. Okay, one-way slab design clause only. Okay, so based on that we choose L by D ratio. When we are talking about two-way slab, it is Lx by D ratio. Okay. So generally, if the Lx by D that is given in code is say 20, now we know there can be some modification factors also that is coming later on. So just to be safe for deflection, we generally choose a factor of 1.5. 25 we start with. Okay, if we require 20, we start with 25, so that later on when the modification factors also come, they after that also we are safe in design. Okay, so we choose the Lx by D ratio. Now we know the D. Step 3 can be to calculate effective span. This can be step 2 also or step 3. Okay, you calculate the effective span. How? By clear span plus effective depth and clear span plus or center to center distance between the supports. Okay, the minimum of which will be your effective span. Okay, so this will be step 2 and this will be step 3. Okay, because Lx will be used now. So these are step 2 and step 3. Now once you got D value, you will calculate, fourth step will be to calculate the factored load. How we calculate the factored load? By sum of live load plus dead load plus floor finish or imposed load, anything, and we multiply this by a factor of 1.5. Okay, so we get the factored load. Once we get the factored load, step 5 will be to calculate the moments. Okay, how we calculate the moment? By first checking what kind of slab it is and what will be the load distribution factor. Now, since it is in simply supported slab which is not restrained, so for this question, our moment factor we will calculate from this table 27. So Lx by Ly ratio will get, and based on that, right now our Ly by Lx ratio is between 1 and 1.1. You will see on calculation it will be between 1 and 1.1. So you can interpolate and get alpha x and alpha y. Okay. So once
Sir,
you
what is the difference between factored load and design load?
design load is generally like what is the actual load which is acting on the structure, and factored load is something what is the safety that we are taking. Now this is a design load. If we are talking about, okay, this is actually what will be acting on the structure, but just to be on the safer side, what code says, multiply this design load by a factor of 1.5, so that you can be safe that your design will not fail.
Means ki if in a question it is given design load is this, then we should multiply it with
Yeah,
1.5 to
yeah,
calculate all the
yeah,
things.
yeah, yeah. It should be clearly mentioned in the question that this is factored load. If it is mentioned factored load, then you don't need to multiply 1.5. If it is
Yes.
not mentioned, then you need to multiply 1.5.
Okay.
Okay. So once you
Okay.
got the factored load and you know the alpha and alpha x and alpha y value, you can calculate moment along both x direction and y direction. Okay, once you get the moment along x direction and y direction, calculate, check for depth. Okay, how we check for depth? By cal by choosing limiting moment will be maximum of mx and my, and based on the limiting moment we calculate d. So d required should be less than d provided. If this is true, then the d that we have provided is safe for one way, one way bending. Okay, else we need to go for both side na doubly reinforce. If this is true, then we are safe for singly reinforced section. That is our under reinforced design criteria. Okay, so if this is true, we are safe. Now the check, when the check of depth is done, what you do, you calculate area of reinforcement and spacing between reinforcement. Okay, so this you will do along both x and y direction. When you will calculate area and spacing, there's two things that you need to check for. Minimum area of reinforcement criteria, you need to check every time. Okay, and minimum spacing, maximum spacing limit. Okay, the both the clause, you know, what is the clause for minimum area of reinforcement? 0.12% of gross area, which is nothing but BD. Okay, and maximum spacing should be less than 3D or 300, whichever is less. Okay, if these are conditions are true, then you have known the area of reinforcement. Once you know the area of reinforcement, you need to just provide the detailing. In the detailing, you need to remember zero point 0.1 Lx and zero point 0.1 Ly. This is the area, this is the distance from the side from which you need to crank the, you need to provide compression reinforcement. Okay, this we saw in the detailing part. Okay, this you can do. So I hope all the steps are clear to everyone of this question. The question is very simple, all the values are given, all the steps you know. I hope you can do this solution on your own now. Any doubt in the solution, like any doubt in the question and how to solve the question? That you also you need to check, sorry I forgot to tell. That you also need to check, we need to check the span to, as mentioned, like, do we need to check this? Then the span between threshold. For example, 1 minute, na? Do slabs. For beams, generally, we don't need to check for depth. Okay, when we were talking about beam design, we didn't talk about control of deflection. I guess in the code it is mentioned that you can check. Okay, just verify it from code. For example, a span is 4 meter and the effective depth is 350 mm. Okay, first convert both the values in meter. Okay, and then do the calculation.
Sir, one thing I want to ask: what is just a if it is asked ki negative movement at continuous age, positive movement at mid span of longer span, negative movement at
Why
continuous
we
age?
say negative? Because when we are talking about the corners, there is bending, like this is the bending moment. Okay, what is that meaning of negative and positive? Now I will tell you. Just wait a second. So suppose this is my beam and this is the load which is acting. So if there is a mid span support, now what can happen, the bending can happen like this and there can be a positive bending at the support also. So that's why we say this is positive or negative, you can say anything as per your convenience, and this is negative or positive opposite to what it is. So that's why we say there is some movement here also and there is some movement here also. So that's why we talk about tension reinforcement also and here compression reinforcement also.
So, sir, we will apply the same formula mx is equal to alpha like
We saw in this question, no? In the first question, we saw this. See here, we calculate alpha x positive, negative, alpha y positive and negative, and we
Sir, actually, I missed it. May I take photographs if you will show
you
just
will
for a while,
you
sir?
will get the slides. You don't need to worry, and you will get the
Okay.
recording also.
When, sir?
Okay, I will just come up to this doubt. So I don't think so. For beam, we need to check for the control of deflection. I will get back to your doubt in the next class because I also have a confusion here of what you are talking. You're true that the depth of the beam is always much higher than the slab. I will get back to your doubt, okay, once. I think that the deflection control we generally do for slab because the depth of the section that we are providing is very small. Okay. When we talk about beam, the depth of the section is so much that we don't need to worry about the deflection much. Okay. I will get back to you. Generally, as per me, we don't check for beam. We check for slab only since the depth of the section is very small in slab. Any other doubt to anyone? If not, I will like close the session now.
When we will get the slides and lecture video?
That I
Like,
guess by NPTEL it will be provided to you. I don't know the details like how they provide. You get the YouTube links, everything from that Soyam portal. Now you can see there. You will get all the informations.
actually, alpha x, alpha y, positive, negative, I don't know how to calculate. Only,
Just go through the discussion that we had today, initial discussion, you will get the solution.
sir, I missed it actually.
Yeah, you can see the recording of the lecture again. Okay, so if there are no further doubts, I will close the session. Okay, so in today's session, we first discussed about design of two-way slab, load distribution, different types of two-way slab, and how bending moment is calculated, coefficients are calculated. Then we discussed about reinforcement detailing, in which we saw cranked up rebars and which how they are provided near support and near the midspan. Then we discussed how steel mesh are designed for to resist torsional stresses when we talk about when we are designing two-way slab under restrained support conditions. And at the end we saw three numericals with different design speculations for understanding the two-way slab design. Okay, so thank you.
Thank you, sir.